we're going to take a look at an example of employing the forward difference, backward difference, center difference formulas for approximating derivatives. And we're going to take a look at various step sizes. And we're finally going to use MATLAB to be able to find the exact values as well to be able to compare. So we have a non-traditional function, x raised to the sine x. And if anybody remembers taking the derivative of this for Calc 1, you would use logarithmic differentiation. Okay, not necessarily a fun technique for most people. And imagine trying to find the second derivative of that thing. That's not too fun at the point x sub naught equals 2. So we're going to approximate the slope, and we're also at step sizes 0.1 and 0.001, and we're going to find the percent error using the forward difference. We're going to do the same thing with backward, and then the center, and then finally we're going to prove a table with all three of the methods. All right, and we're going to produce everything in a table. All right, so first things first, let's create some sims variables because we're going to need some derivatives. So I'm going to create a sims of x and f, and I'm going to define my function f to be x raised, and I'm just going to use dot raised to the sine of x. All right. And the only reason I'm doing the dot is just in case we want to use more than one value in that, we can. Although in this example, we're probably not going to do that. Okay. Now at this point, what we can do is we can find the derivative, and I'm just going to call that deriv. So the derivative, and by the way, this is not helping with the numerical part. It's getting the actual answer. Okay, so the derivative is going to be equal to, remember their function diff. So we're going to take the derivative of f with respect to x. Right? And then finally, we can find the actual value when x is equal to 2. So we're going to say the actual value is going to be when we substitute back into the deriv. We're going to substitute for x, and we're going to get 2 out of that. All right. And if I just go ahead and run that really quickly, just to illustrate, it gives us this weird number. All right. It doesn't give us like an approximation, but this would be the derivative at 2. All right. It's not a nice derivative. Now, let's go ahead, and now that we know the actual value, let's start utilizing our formulas. Okay. So if we go back and we're going to use the forward difference method. All right. So we need to take the next x minus the current x divided by h. And we're going to have two different step sizes. All right. So let's do this. Let's call x sub I equal to 2. And let's call h1 equal to 0.01, because that was our first step size. And let's call h2 equal to 0.001. Obviously, as the step sizes get smaller, we should get a much better approximation for the derivative of this. I'm going to call forward diff 1. So this is the forward derivative of the first type of 0.1. Now remember, that's going to be equal to, and we're going to use this formula. Okay, so I'm going to do my best to kind of keep this formula on the screen as I'm typing if I can. All right. Just position this. Maybe it'll work. Probably not. Okay. So just keep that formula handy. But we're going to need the next x. So that's going to be when I substitute back in. So I'm going to substitute into the function. All right. So I'm just taking the original function. The original variable was x. And what I'm going to do is I'm going to substitute x sub I plus h1, the step size. All right. So this is the next x right here. From that, I'm going to subtract the current x. So that's going to be f comma x sub I. And then I'm going to divide all of that by h. And in our case, that's h1. Now, I'm just going to let this roll real quick. All right. And it gives us this value, which we have no idea if it's anywhere close. All right. That's okay. I'm going to copy and paste this and check this out. For f diff 2, and again, what we're doing is we're trying to find the derivative at 0.001. All I'm going to do is I'm going to just change these to h2 because I've set it up once. And this is going to be h2. All right, now, the real moment of truth comes when we start being able to determine what the percent error is. Okay, and again, if I was to run this, which I will really quickly, we're going to get an answer that, well, actually, we're not going to get any answer. This should be x sub I, excuse me. But we're going to get an answer that doesn't really mean much to us. All right. unless we're a supercomputer and we can crunch that in our heads. And if we were, we're probably not taking this class, we're probably teaching it. So let's go ahead and create a table. So I'm going to do an fprintf. We're going to have, first of all, the actual value. Right? And then let's have our step size. And then we're going to have the forward difference approximation. And then finally, we are going to have the percent error. All right. And I guess we actually need to compute the percent error before that. So let's compute 2% errors. Okay. So I'm going to call this F error 1, forward error 1. And that's going to be equal to the absolute value of F diff 1 minus the actual divided by the actual. And we're going to multiply that by 100, all right, to get our percent error. And then I'm going to do the exact same thing to get our second error, all right, and this is the one where step size is smaller, and I'm just changing that in 1 and 2. All right, so now we can do our fprintf, and I should include this /n here. So we're going to finally do our fprintf, and this is the moment of truth where we finally get to this. So we're going to have a percent f for the first actual. We're going to have our step size, and we're going to have our f diff approx, and then we're going to have our percent error. All right, and we're doing this first of all for the point for the point 1. All right, so now the parameters I'm going to be calling are going to be the actual value, the first step size, which is h1, the forward difference, I'm going to call that f diff 1. All right, so that's this guy right here. And then finally, the percent error for the first one, so that's FERR1. All right. Now I'm going to copy and paste this, and surprisingly, all I'm going to have to do is just change everything to 2s. All right, so this is going to be a 2, 2, and a 2, and that's actually going to tell us what the forward difference is for using the H2. All right, so let's run this and let's see what we get out of it. Hopefully something, and hopefully something good. All right, and that might be the closest I've ever done to actually lining up the tabs or the headings. So let's bump up the step size just a little bit, and we'll have to backspace this. All right, let me run it one more time. Again, this is just setting it up. All right, there we go. Now, I want you to notice that when the step size is 0.1, the actual value is the actual slope, or the actual derivative is 30 or 0.3121, and we get 0.19198, so 192. That's pretty far off. So we get almost a 39% error. But when we start going through and utilizing the step size at a much smaller size, 0.001, we get a much better percent error. Okay, so that's pretty cool. This one's less than 1% error. And you can imagine if I were to just change this a little bit more into 001, that the percent error is even less than that. All right, now the problem asks us for this. All right, so the good news is that once I have this, and what I'm going to do is I'm just going to do a couple spacers here. Once I have this set up, then all I have to do is just copy this, the entire thing, and I can just recode some of this to get the backward difference as well as the center difference. Okay, so now remember our formulas. Okay, so for this, the backward difference, all we're going to do is we're just going to change this, the fx sub I plus 1 to fx sub I, and then the next one to f sub x sub I minus 1. All right, so right here, now I'm going to call this b diff. So I'm going to change all these f's to b's for backward. And this is just going to be x sub I, and this is going to be x sub I minus 1. And then I'm going to do the exact same thing. And actually, this is going to be x sub I minus h1. And this is going to be x sub I minus h2. All right, so that was really easy to change. We're just going to change this to back diff. and back diff. And then right here, we're just going to change this to back diff. And we're just going to change these to back diff, and from F forward error, this is our backwards error. All right, so really, really easy for us to do this. All right, we're going to run it, and this is going to give us the backwards difference. And I should probably do F print F if I'm going to make this run correctly. All right, now, not much difference in the errors. The backwards difference is a little bit better, all right, especially when the step size is small. All right, it knocks off almost 2% error. Right here, it really doesn't make much difference. It's almost negligible. All right, let's do it one more time for the center difference. All right, so pretty cool so far. We're getting really close just by using a fairly good step size. And now we're going to use our center difference. Now this just takes x sub I plus 1 minus fx sub I minus 1. All right, divides it by 2h this time. All right, so we're going to copy and paste again. And we're just going to say fx sub I plus h1. And we're going to have fx sub I minus h1. And we're going to change this to 2 times h1. All right. And then we're going to do the exact same thing, except with h2s. All right, so we're just going to change this to plus h2. We're going to change all of our backwards difference, b diffs, to c diff. And from b error to c error, centered error. And our c difference right here, I'm going to change this to a centered difference. And right here, I'm going to change these to c's. And I'm going to change this B to a C and this B to a C. All right, so let's see if the center difference has any significant difference on the error. And we had, at best, we had about 0.38 error, okay, 3738. So let's see what happens if we use the center difference. All right, now with the center difference, notice we changed this from 38 to 36 to 1% error. And then down here, there's almost no error. In fact, if you take a look at the actual and the center difference, they're almost spot on. Okay, so really cool that we can go through and use this numerical differentiation to take a fairly ugly function like this, all right, that we don't usually work with, and get some pretty good numerical derivatives out of it. All right, now, the last thing that we were asked to do is we were asked to produce a table. All right, and the table is going to find the slope at all three methods with h at 0.001. So we're going to do one last f print f, and we're going to have, let's just have the actual, let's have the forward difference, let's have the backward difference, and let's have the center difference. All right, and we were doing this for step size h is going to be 0.001. So we're going to print, now we're going to have 4% Fs. And backslash n, and our parameters are going to be actual. We are going to have the forward difference 1 or 2, excuse me. We're going to have backwards difference 2. And then finally, we're going to have the center difference 2. Right? And that should do it for us. So now this might be misaligned a little bit. So of course, I'm going to sit here and try to make it look good. It would be helpful if I can change my T to an F. All right, and let me just space this out just a little bit, just to say that I did it. Let's see if that helps any. And I'm looking at that last line of code. All right, there we go. And right here, we can really see the disparity between the actual, and this should just be a forward difference F diff. All right, so that might change the lining a little bit, not that much, but really what this does is this helps us to give a good comparison on the eyeball test on the different types of difference formulas. All right, so can we employ this method to look at second derivatives and even higher order derivatives? And of course, the answer is yes. And what we're going to do in the next video is we're going to explore how we can go ahead and numerically approximate the second derivative. And then we're going to look at improved methods for finding numerically finding the derivative.